Institute of Aeronautical Engineering, Autonomous Dundigal. This is my tech talk. My name is N. Venkat Sai, roll number 23951802226, subject Sustainable Energy Systems. Topic Explain wind turbine classification and selection criteria. Department Electrical and Electronics Engineering. Understanding wind turbines, classification and selection, a comprehensive guide to wind turbine technology classification system and selection criteria for renewable energy projects. Why wind power? Global energy transition. The renewable revolution. Wind power has emerged as a cornerstone of the global transition to clear energy. With wind energy capacity exceeding 900 gigawatts worldwide in 2023, turbines now generate over 7% of global electricity demand. The International Energy Agency projects wind capacity will triple by 2030, driven by climate commitments and declining cost. Strategic advantages. Wind energy offers distinct advantages: zero operational emissions, minimal water consumptions, and increasingly comprehensive economics. Unlike fossil fuels, wind power provides energy security through domestic resource availability. Modern turbines operate efficiently across diverse climates, from Arctic regions to tropical zones. 900 plus gigawatts installed. Global wind capacity exceeds 900 gigawatts. 7% world electricity share to global power generation. 1.3 investment by 2030. Projected cumulative investments. Horizontal axis wind turbines. Dominant designs. Horizontal axis wind turbine represent the industry standards, accounting for over 95% of global installations. Their aerodynamic design maximizes energy capture through rotor blades that rotate perpendicular to the wind direction. Rotor blades. Three blades typically span 80 to 150 meters, designed using aerospace engineering principles to optimize lift, minimizing drag. Gearbox system, increasingly rotating speed for 10 to 20 rpm at the rotor at 1000 to 100 rpm for generating efficiency. Electrical generator converts mechanical energy into electrical energy, typically 2 to 15 megawatts capacity per turbine. Yaw mechanism rotate equal to phase changing wind directions, ensuring optimal energy captures. Vertical axis wind turbine. Key applications. Alternative configuration. Vertical axis turbines positions the main rotor shaft vertically with blades rotating around the axis, less efficient in HVWs and vertical axis wind turbines. Offer unique advantages and specific applications. Key characteristics. Unidirectional operation without yaw mechanism, lower center of gravity, improper stability, access for maintenance and ground level, reduced visual impact and noise emissions, compact design and shoot urban integrations, off-grid applications, hybrid systems. Key classification criteria: size, power, and applications. Wind turbines are categorized by power output and application scale, each surveying distinct market segments with specific technique requirements. Micro turbines, small scales, medium scales, utility scales, residential and small business. Micro and small scale turbines provide on-site generation at homes, fans, and small commercial properties. Community projects, medium scale installations serve the community energy schemes, schools, and municipal facilities. Utility power plants, large turbines from commercial wind feeding transmission grids. Site site assessments, wind source, topography and environment. Wind resource analysis, long-term methodology data, established average wind speeds, turbine and wind shear profiles, topographic evolution, hills, valleys and coastal features significant influence with wind patterns, environmental constraints, wildfire coordinates and protected habits and noise sensitive limit turbine placements. 6 plus meters per second minimum annual average for variable projects. 80 meters altitude typically hub height for optimal wind capture. 300 days monitoring minimal days collecting periods. Technical specification, rotor diameters, hub height and cut-in cutoff speeds. Key technical parameters determine turbine's performance and compatibility with site conditions. Understanding this specification enables informed select decisions. Rotor diameter, hub height, cut-in speed, rated speed, cutoff speed. These parameters instruct complex to large rotors at greater height, captures more energy but requires robust structures, design higher cutoff speed and safety. Economic considerations, capital cost, O&M and LCOE. Financial viability depends on upfront investments, ongoing expense and long-term energy source cost. Levelized cost of energy provides the comprehensive metric for pairing alternatives. Capital expenditure, turbine purchase, transportations and installation cost typically 1 to 2 millions per megawatts for land-based turbines, 2 to 3 millions per megawatts and offshore installation. Operating and maintenance, regular inceptions, component replacements and repairs. Annual ON operating and maintenance cost average 30,000 to 50,000 per megawatts, increasing over turbine lifetime. Levelized cost, present value of total lifetime cost divided by the energy output. Modern wind levelized cost range 30 to 50 megawatts or competitive with fossil fuels. Cost breakdowns, turbine equipment 60 to 70%, fundamental and civil works 15 to 20%, grid connection 8 to 12%, installation 5 to 8%, development and permits 3 to 5%. Revenue streams, electricity scale to grid operation from primary revenue, additional income from renewable energy certificates, capacity market and ancillary service enhance economics. Environmental and social impacts, noise, visuals, and wildfire. Wind turbine deployment requires carefully consideration for environmental and community impacts, proper setting and mitigation measurements, minimizing advice effectively. Noise emissions, mechanical and aerodynamic noise typically measure 45 to 55 database and 350 meters distance. Modern designs incorporate and quickly gearbox and blade profiles like distance from the residence reduce community coupling. Visual impact, turbine visibility effect, landscape characteristics and property values. Showed of flicker drawings, sunrise sunset periods may concern nearby residents. Carefully turbine placements and color selections reduce visual interactions. Wildlife interactions, electromagnetic interference, habit fragmentation. Across roads and infrastructure, alternate local ecosystems, restoration programming, and wildlife coordinates mitigates habit description. Offshore installation create artificial reef effect benefiting make relief. Community engagement, local oppositions, challenges, projects, community benefit schemes, shared ownership modes, and transparent consultation process build public supports. Selecting to right turbine, a decision making framework. Systematic turbine selections balance technical requirements, economic constraints, and environmental considerations. This framework guides optimal choice for specific project contents. Define project objective, establish capacity target, budget limits, and timeline constraints. Conduct site assessment, measure wind resources, evaluate topography, and identify constraints. Evaluate turbine options, compare technical specifications against site characteristics. Analyze economics, calculate playback periods and return on investments. Assess environmental impact, conduct AS and development mitigation strategies. Engage stakeholders, consult communities, regulators, and grid operators. Finalize selections, choose turbine models balancing all criteria. There are 7 types. Key takeaways, successful turbine selection requires holistic evaluation rather than focusing solely on lowest cost of highest capacity. optimizing for specific site conditions, grid requirements, and stakeholders' expectations delivers superior long-term values. Thank you.